Hello everyone, this is a summary for Chapter 19, First Law of Thermodynamics. Let me just make sure my microphone is on because I just finished a 40-minute recording of this same Chapter 19 summary and the microphone was off and it is on, so it's all good. Alright, so let's start with section 19.1, Thermodynamic Systems. Basically, in this section, it just is saying that we have a certain system, like a popcorn kernel, and if we add heat into the system, which is Q, we end up with some sort of work done by the system, right? So in the case of the popcorn, the pressure pushes a kernel shell to pop, right? And yeah, it's just an intro to this chapter. All right, so moving on to chapter 19.2, work done during volume changes. So previously, we calculated work as the integral from x naught to, or initial x to final x of a force along dx, right? Okay, and that was the area under this curve, the force curve, that was work. In thermodynamics, we still use that same formula, which is work is equal to the integral of force along dx. We just change things up a little bit, okay? And let's look at this picture right here of a piston, right? So we have molecules of gas. Those are those little green particles moving in random directions. And those molecules of gas hit the face of the piston on this side, right? So we have a force of gas. And we also have the environment with molecules in the air hitting this face of the piston, pushing that way, and that's the force of the environment, okay? And if our piston moves, right, we have a displacement of our piston, then we have work, okay? And as we can see, the force from the gas particles, these green molecules of gas, is the opposite direction of the force of the particles from the environment that hits the piston on the other side, right? So when we have a displacement or the piston moves, we have work. So as we can see, because of the various or the opposing directions of the forces from gas and environment, we have that the work done by the system is equal to negative the work done by the environment. Okay, they have the same value, just opposite signs. One is positive, then the other is negative, and vice versa. Okay. All right. Now, let's look at work. How we calculate work, right? I said we calculate work by getting the integral of a force along dx. Okay? Well, what is force? Right? First, what is pressure? Pressure is equal to a force over an area, right? And so we can rearrange that to say that force is equal to a pressure times an area. Okay? And that's what we did here, right? Instead of force, we put pressure times area. Okay? It's the same thing because here it says they're equivalent, right? Okay, what is the area we're talking about? In the case of a cylinder, right here, this is a cylinder with a cross-sectional area, let's call this A, yeah? This cross-section, that's area, that's equal to A, which we have here. And if you multiply that area along the height, that cross-sectional area along this let's call this X, right? This height, that would be the volume of the cylinder, right? So another way of writing this is calling it dV, right? So for this chapter, or in our case, we'll say that work done by the system is equal to pressure, which is here, times these two, area times dx, which is volume. So then we have dv, right? Okay, so the work done by the system is equal to the integral from initial volume to final volume of the pressure, okay, in dv. And that is symbolized by the PV diagram right here. We have an initial state and a final state. And we're going to get the integral of this pressure along this volume, right? So then that's this area right here, which is work, area under the curve. All right. Some good things to know in section 19.2. If the direction of force is the same direction as the displacement, then the work is positive, right here. And if the direction of force is in the opposite direction as the displacement, then the work is negative, okay? So let's look at our piston example. The direction of the force is, for our system, or gas, is the same direction as the piston moves, right, to the right. Then the work done by the system is positive, okay? Now let's look at the work done by the environment. The work done by the environment goes towards the left, and the piston goes towards the right. That's where our dx is, moves to the right. Our piston moves to the right. So as a result, in that case, the direction of force from the environment is the opposite direction as the displacement of the piston. So the work done by the environment in that case is negative, okay? That's all it is. Okay, section 19.3, it's fairly simple. Just basically in a PV diagram, we have states, okay? We move from state to state. So we're looking at the paths between thermodynamic state. That's, oops. This is the path, right? And these are the states, 1, 2, and 3. Though it's represented by the dot in the PV diagram, okay? And we are looking at how we move from state 1 to state 2, and how we move from state 2 to state 3, the paths between the states. All right, and the variables needed to form a state is pressure, volume, and temperature. Okay, just remember the ideal gas law from the previous chapter. That is PV equals nRT. We're going to be using that in this chapter as well. And as long as you know the number of moles, right, that's N. If you know the number of moles, and you can look at the PV diagram so that you could read the pressure and the volume. So let's say for state 1, you could read pressure, the P1, and V1, right? Or if you wanted for state 3, then you could get V3 and P3, right? And so once you find the pressure and volume from the PV diagram, you could calculate the temperature using the ideal gas law right here, okay? There are 3 processes often used to transition between states. That is the isothermal process, when you have constant temperature. Second is the isobaric process, when you have constant pressure. And third is the isochoric process, when you have a constant volume. And we'll expand into that in later chapters, which we'll do shortly. All right. Another thing to note, in a sealed container, from the ideal gas law, we have P1 times V1 over T1 is equal to pressure 2 times volume 2 over temperature 2. And that's also equal to pressure 3 times volume 3 over temperature 3. All right. Okay, moving on to section 19.4, internal energy and first law of thermodynamics. So the first law of thermodynamics is the change in thermal energy, right here, is equal to heat transferred into the system plus the work done on the system by the environment, all right? And remember what we talked about in 19.2, work done by the environment is equal to the absolute value of work done by the system, but they just have opposite signs. So whatever the work done by the environment, that is equal to the negative work done by the system. All right. And when is work done by a system positive? So work system, sorry, when is work system positive? Work system is positive when work is done by the system. Then it's positive. All right. Work system is negative when the work is done on the system by the environment. Okay. And for Q, heat transfer, it's positive when heat goes into the system. Heat is going into the system, and it's negative when heat is leaving the system. Okay. All right. And just some common types of thermodynamic processes. The first one is cyclical process. And that just means that the start and end, the starting state and the ending state are the same point in the PV diagram. Okay. And you can see that here, right? Our states 1 and 2 is the same blue dot, right? So they start and end at the same point in the PV diagram. And for any cyclical process, we have our initial temperature is equal to our final temperature. So therefore, our change in thermal energy is 0. All right? So if we write the first law down, change in thermal energy equals heat transfer minus work done by the system, because our change in thermal energy is equal to 0, that can be rewritten for a cyclical process as heat transfer is equal to work done by the system. Okay? All right, for isochoric process, which means a process where we maintain constant volume, right? As you can see here in this picture, we have a fixed volume. And if we add heat into the volume, because the volume is fixed, our pressure will have to rise. And that is, our P2 is greater than P1, right? And that is evidenced by the ideal gas law, PV equals nRT, right? If we know that N and R are constant, right, in this fixed volume, and volume is constant because it's fixed, so we have P over T equals some constant, right? And so because this is constant, if we increase T, or we increase the temperature, then we are also having to increase the pressure, right? Also, because this is constant for state 1 and state 2, we'll get that P1 over T1 is equal to P2 over T2 for an isochoric process, or a process with constant volume. What else? A work done by the system is equal to 0 for an isochoric process, right? Because remember that work is the area under the curve, and this is just a vertical line, so there's no area under that curve. So looking at the first law, change in thermal energy equals heat transfer minus work done by the system. If work done by the system is 0, right, because this is a vertical line, the area under the PV curve is 0, then therefore the change in thermal energy is equal to heat transfer for an isochoric process, or a process with constant volume. Okay? The next process we're going to talk about is the isobaric process, which means a process with constant temperature. And usually these are problems like if we have a cylinder with a piston inside and a certain volume, right? And the piston is free to move, frictionless, and it's free to move. And we add we add some sort of heat transfer into the system, usually, let's say, fire. And the piston is free to move, so volume can increase, so our pressure remains constant. What that looks like in a PV diagram is a horizontal pressure line, right? Because pressure doesn't change. It's just constantly whatever this P value is. Okay? So the work for an isobaric process, or a process with constant temperature, would be the area of this rectangle. Okay? And that would just be P times delta V, or P times V2 minus V1. That's this area right here. Okay? All right. For an ideal gas law, PV equals nRT, and a constant pressure or isobaric process P would be constant, N would be constant, and R would be constant. If I rearrange that ideal gas law formula to have the constants on the right side of the equation, our constants would be nr over p. These would not change from state 1 to state 2. Okay? So as a result, V1 over T1 would be equal to V2 over T2 because they're both equal to this constant nr over p. All right? And that's only for an isobaric process. And also, since the work is the area under the triangle, for an isobaric process, if we're, let's say, using the first law, the work done by the system is equal to P delta V, right? This is delta V, V2 minus V1 times P. So that's this area right here. Okay, and that is this formula for an isobaric process. Work done by the system is equal to pressure times final volume minus initial volume. Okay, for isobaric process. What else? So also for an isobaric process, our heat transfer Q is equal to N, which is our moles, our amount of substance in moles, times Cp, which is our molar heat capacity at constant pressure, times delta T, which is our change in temperature, okay? And that is the heat transfer only for an isobaric process, all right? By the way, guys, everything I have in the red box right here, those are things that I think you should have in your formula sheet because it'll help you with your homework, your practice exam, or especially during the exam. So these are things that I hope you guys understand the concept too, but also it's important just to have in your formula sheet, everything with a red box around it, okay? Also, in any other process, this is true for all conditions, right? Not just an isobaric process, but all processes. Heat transfer is equal to moles, N, right, which is our moles, CV, which is the molar heat capacity at constant volume, and delta T, which is a change in temperature, okay? And the final process we're going to talk about is the isothermal process. And that just means constant temperature, a process with constant temperature, okay? And as you can see here, we're in the same isothermal curve. So our temperature at state 1 is the same as our temperature in state 2, okay? If we look at the ideal gas law, PV equals nRT, because our temperature is constant, our R is constant, and N is constant, for an isothermal process, when we have constant temperature, we can say that P1 times V1 is equal to P2 times V2, right? Because they're all equal to nRT right there. Okay. What else? The work is the area under the curve, right? So the work of the system is equal to the integral of pressure from V1 to V2, right? But remember that the ideal gas law, PV equals nRT, I can change that around to make pressure equal to nRT over V. And then an isothermal, we just said that temperature is constant, R is constant, and the number of moles is constant. So if I plug that in here for pressure, nRT over V, and bring my constants outside of my integral, I'll have nRT, which is a constant, or the work done by the system is equal to nRT, which is a constant, times the integral of 1 over V from V1 to V2, right? And what is the integral of 1 over x? It's ln of x, right? So in this case, this formula becomes, or this equation becomes, work done by the system is equal to nRT, which is the constant, times ln of Vn over V1, or V2 over V1, sorry. Okay? So the work done by the system for an isothermal process is equal to nRT times natural log of V2 over V1. Okay? What's another way of writing this? Because nRT is a constant, and we know that this constant is equal to PV, then we could also say that the work done by the system is also equal to PV times the natural log of V2 over V1. Okay? In an isothermal process, since there's no change in temperature or change in thermal energy, our change in thermal energy is 0. So then our first law for an isothermal process just simplifies into heat transfer is equal to work done by the system. Okay? All right, we're getting towards the end, just a little bit more. Chapter 19, Section 6, Internal Energy, also known as thermal energy. The internal energy of an ideal gas depends only on its temperature, not on the pressure and not on the volume. Okay? And the formula to calculate internal energy, or delta ETH, is equal to N, which is the amount of substance in moles, times CV, which is the molar heat at constant volume, times delta T, which is the change in temperature, right? We talked about this in the, I think it was here, and we talked about this in the last section. But we'll talk about it again because it's not too long. Anyways, so that is the formula to calculate the change in thermal energy. Okay, NCV delta T, and that is true for any process. Okay, isothermal, isobaric, isochoric, all process. Okay. Another important thing to know is heat transfer, and this is only true for isobaric. Okay, so this is only true when you have constant pressure. Heat transfer is equal to the amount of substance, or N in moles, times the molar heat capacity at constant pressure, Cp, times change in temperature. Okay, again, that's only true for an isobaric process. Okay, molar heat capacity for solids. So for solids, you could find heat transfer using mass or moles. Okay, so you could use mass m, tiny m, and or moles, tiny n. Okay, so heat transfer for a solid is equal to mass times specific heat times change in temperature. All right, that is what the heat transfer is for a solid. Okay. And for a gas, it's amount of substance, or mole, times molar heat capacity times delta T, or change in temperature, right? And you can, here are just a couple of equations that allow you to see or move between molar mass and mass, or molar mass and moles, as well as molar heat capacity and molar mass and specific heat, okay? So molar mass is equal to mass over amount of substance, in N, okay? Or the moles, right? And molar heat capacity, or capital C, is equal to molar mass times little c, specific heat, okay? These are, again, just two equations that will allow you to find molar mass if you're given the mass, or find mass if you're given molar mass, or find moles if you're given molar mass, right? It's just a formula to go between one and the other, okay? And same with molar heat capacity and molar mass and specific heat, right here. Okay, quickly, what the units for molar mass and molar heat capacity and specific heat capacity. For molar mass, the unit is kilograms over moles. Could also be grams per mole, right? And any unit of mass over mole, right? For specific heat capacity and molar heat capacity, they're both joules over mole times Kelvin, okay? That's just the units for those guys. All right, chapter 19, section 7, molar heat capacity for ideal gases. Looking at these two curves, right, from T1 and T2, I can transition from this curve to this curve either isochorically or with the same volume, right, V1, or isobarically with the same pressure, this horizontal pressure, right, with P1. Okay. And for an isochoric process, again, we've talked about this earlier, so I won't delve into it too much, but looking at the first law, change in thermal energy equals to heat transfer minus work done by the system. As you can see in an isochoric process, right, constant volume, it's a vertical line. So the work, there's no area under the curve, so work is 0. So the change in thermal energy is equal to Q, right? And again, remember the change in thermal energy is equal to N, or moles, times molar heat capacity at constant volume, CV, times change in temperature, delta T, right? And that is true for any process, right? That's what we talked about right here in 19.6. Okay. For an isobaric process, right here, when pressure is constant, well, we can't really cancel out anything in the first law of thermodynamics, right? Delta ETH equals Q minus work done by the system. But we can substitute things. So like we said, for an isobaric process, right, Q is equal to moles times molar heat capacity at constant pressure times change in temperature. Okay. So let's substitute Q for that, or our N Cp delta T. And again, for a isobaric process, what exactly is the work done by the system? It is this area of the rectangle, right? Which is our pressure times V2 minus V1, right? That's this rectangle area right here. Okay. Another important relationship between, or another important equation to know, again, that's why it has this red box around it, is a relationship between the molar heat capacity at constant volume and molar heat capacity at constant pressure. Okay, so the molar heat capacity at constant volume, CV, is equal to the molar heat capacity at constant pressure, CP, minus R. Okay, that's just an equation you should know so that you could get to CV from CP anytime you want, or you can get to CP from CV, right? Because R is constant, and you guys should know that value by now and have that value in your cheat sheet somewhere. R doesn't change, all right? And the last equation I think you guys should know from chapter 19, section 7 is the ratio of heat capacities, which we use the symbol gamma for. And the ratio of heat capacity, gamma, is equal to molar heat capacity at constant pressure over molar heat capacity at constant volume. Okay? And another thing to know is that gamma is always greater than 1, right? That's because of this equation right here. As you can see, molar heat capacity at constant pressure is greater than CV because Cp, molar heat capacity at constant pressure, minus the constant R is equal to CV. So Cp is always greater than Cv, so as a result, gamma is always greater than 1. All right, we are towards the end of this chapter. I really hope I recorded everything with a microphone on this time. All right, chapter 19, section 8, adiabatic process. Adiabatic just means that no heat transfer occurred in that process, okay? So adiabatic means no heat transfer. And whenever there's no heat transfer, Q, which is heat transfer, equals 0, right? So whenever you see an adiabatic process occur, Q is equal to 0, all right? Some keywords to know. In your problem, when you read that something happens really fast, Okay? That's a key word to know that that was an adiabatic process. So there was no heat transfer and your Q is equal to 0. Okay? And in the problem, if you read that something happened really slow, then it's an isothermal process. Okay, so no change in temperature happened between state 1 and state 2, so change in thermal energy is equal to 0. All right? I know isothermal is not part of 19.8, right? We're just talking about adiabatic process for chapter 19.8, but I just wanted to give you guys a keyword. When you see something really slow, that means it's isothermal, okay? But when it's really fast, it's adiabatic. All right, so looking at the first law of thermodynamics, right? Change in thermal energy equals heat transfer minus work done by the system. Like we said, in an adiabatic process, Q equals 0. So as a result, because Q equals 0, our first law simplifies to change in thermal energy is equal to negative work done by the system, right? Again, that's because Q becomes 0. All right. So let's look at the ideal gas law and what that we can simplify in an adiabatic process. Well, our constants are just N and R, right? So if we move the constants to the right side of the ideal gas law equation, we get PV over T is equal to NR, which is a constant. So from all states, state 1 and state 2, PV over T is equal to NR. So as a result, P1 V1 over T1 is equal to P2 V2 over T2 for an adiabatic process. Okay? All right. And lastly, just these two equations are important because they are equations with gamma involved, or the ratio of molar heat capacity. So P1 times V1 to the power of gamma is equal to P2 times V2 to the power of gamma. Okay? It's just something you should know and have in your cheat sheet. T1, initial temperature times initial volume to the power of gamma minus 1 is equal to final temperature over final volume to the power of gamma minus 1, right? Okay, that's another formula you should know. And again, just recall that gamma is only Cp over Cv, right? The molar heat capacity at constant pressure over the molar heat capacity at constant volume. All right, and to end this lecture, I just want to state the value of the ratio of heat capacity, gamma, changes depending on the type of gas you have. So if you have a monatomic gas, the value of gamma is 1.67. Okay. For a diatomic gas, the value of gamma is 1.4. And for a polyatomic gas, the value of gamma is 1.3. And usually they will let you know or make it very obvious whether you're dealing with a monatomic gas, diatomic gas, or polyatomic gas. All right, guys. That's it for the chapter summary of chapter 19. I hope that helped you guys. I do like making these videos, and I hope they do help you. And the only thing is that I can't release the problem set videos, the problem set solution videos, as fast as I'd like to when I do make the chapter summary videos, because as you can see, this is a lot of, it takes a while and it's quite a bit of work. So let me know either in the comments or let the professor know if you guys prefer to have a chapter summary video released before the videos for solutions of problem sets, or if you guys just want to get the solutions for the problem set videos released as soon as possible, then I could just skip the chapter summary and keep, so I could get to working on the problem set solution videos and release those quicker. Let me know what you prefer and what helps you out better. All right, have a good day.